Bismillah ar-Rahman ar-Rahim. We're still in chapter 6, talking about the solution of boundary value problems in electrostatics. So we take up an example of capacitors in parallel in Cartesian coordinates, two parallel plates with the space between them divided into two dielectrics, epsilon and epsilon 2. Here we solve Laplace's equation, which is one-dimensional. Del square V becomes d second V dz square equal to 0, with boundary conditions V of 0 equals V naught and V of z equals d equals 0. The solution is V of z az plus b, with b equal to V naught and a minus V naught over d. So this is the solution. Then we have the interface boundary condition, which is the continuity of tangential E on z equals 0, which is Ez. Okay. The boundary condition at z equals 0 is rho s1 equal to epsilon 1 Ez for medium 1, which is epsilon 1 V naught over d, Coulomb per square meter, and for medium 2, rho s2 is epsilon 2 V naught over d. The total charge is thus Q equal to rho S1 times the area S1 of the first plate plus rho S2 times S2, giving the capacitance C equal to epsilon 1 S1 over D plus epsilon 2 S2 over D, which is the capacitance of two capacitors in parallel. Another example on capacitors in series. We take the capacitance between two cylindrical capacitors, two cylinders, cylinder of radius A and cylinder of radius C, with the space between them divided, in region 1 of radius B, having epsilon 1, and region 2 having epsilon 2 between B and C. Here the boundary conditions are V of rho equals A equals V naught and V of rho equals C equals 0. So it is a one-dimensional Laplace equation which reduces to dd rho of rho dv d rho equals 0. The solution in region 1 is V1 was A1 ln rho plus B1, and the solution in region 2 is V2 equal to A2 ln rho plus B2. Now we have four boundary conditions here because we have four arbitrary constants. The first boundary condition is at rho equals A, V naught equals A1 ln A plus B1, and the second is V at rho equals C equals 0, giving 0 equal to A2 ln C plus B2, equation 2. And the continuity of the potential at rho equals B gives V1 equal to V2, which is equation 3. Then the other condition at the interface rho equals B is continuity of normal D, which gives epsilon 1 E1 rho equal to epsilon 2 E2 rho. By calculating the derivative of V, or the gradient of V, we have E1 rho and E2 rho, and this gives us equation D. We can rewrite these equations as follows. And then we can eliminate one of the unknowns, A2, and then we have a system of three equations which we can write in matrix form, and we can solve this by Cramer's rule. We only need to solve for A1 in order to find the total charge on the inner conductor of radius A. Thus we find A1 is given by this equation. Then the charge per unit length on the inner conductor is simply rho L equal to 2 pi AA times rho S, okay, which is this. Now the capacitance C is simply rho L over V naught, which is in farads per meter, and we can arrange it in this form, and you see that it is the capacitance of two capacitors in series, C1 and C2. Okay, here are C1 and C2. Okay. Another example on capacitors in parallel is in spherical coordinates. We take up two spheres of radius A and B with the space between them equally divided, with epsilon 1 in the region z less than 0 and epsilon 2 in the region z greater than 0. From the boundary conditions, V of R equals A equals V naught and V of R equals B equals 0, Laplace's equation is one-dimensional, function of only of R, and del square V equals 0 becomes d dr R squared dV dr equals 0. Solution satisfying the boundary conditions is V of R equal to minus A over R plus B, where A is minus AB V naught over B minus A. The electric field is minus dV by dr, the gradient, negative of the gradient of V, given by this equation. And the continuity of tangential E leads to the total surface charge on R equals A. And here it is divided between the region 1 and region 2. So the total rho S is rho S1 plus rho S2 times the area, okay, times the area. So the total charge Q is this, and you can see it's divided into two parts. So this is the capacitance of two capacitors in parallel, and if epsilon equals epsilon 2, we get the capacitance between two spheres, which is 4 pi epsilon 1 over 1 over A minus 1 over B. And if B goes to infinity, we get the capacitance of one sphere, which is 4 pi epsilon naught A. Well, in the next lecture, we are going to talk about the capacitance between two parallel cylinders, which is the capacitance of the parallel wire line, of the two-wire line.